Hi, and welcome to Chapter 13. In Chapter 13, we're going to go over a concept called business intelligence, and then we'll explain about data warehousing. It's just a different way of storing a database, but business intelligence is really quite important. When you get into the real world, being able to analyze your data and be able to provide knowledge to your customers is part of the whole reason why databases are wonderful to begin with. So understanding business intelligence is going to be pretty important. Let's get started. The first thing we're going to talk about is what is business intelligence. So business intelligence, as a definition, is comprehensive, cohesive, and integrated set of tools and processes used to capture, collect, integrate, store, and analyze data with the purpose of generating and presenting information to support decision making. Okay, big, long, huge description to simply mean ability to use the data to give information to decision makers so they can make good decisions. You need to find a way to get your data out of the database and turn it into something useful, because we want our business decision makers to be able to make accurate decisions based on the data that you've stored. So you stored all this data in your database. Great. That doesn't do me any good if I can't get data out, if I can't get knowledge, if I can't get information from the data that's in the database. So the whole purpose of business intelligence is being able to take that data and turn it into something useful. Okay, when you follow the process of data intelligence, developing data intelligence or business intelligence, we follow this kind of circular process. First, we collect and store your operational data. Now, operational data is going to make more sense in a few more slides where we describe the difference between operational and some decision data. But operational data is just your day-to-day information that goes into your system. So this is all the operation. We're going to store invoices, we're going to store inventory, we're going to take stuff out of inventory, we're going to be changing things around. What are we doing with our data over time? This is the collecting and storing part. Next, we're going to aggregate that data, that operational data, into support data. So we're going to change it from just data in and out into something supportive. So aggregating usually means one of those aggregate functions. So when you hear the word aggregate, first thing you should think of is sum, count, average, min, max. Those 5 things when you think of aggregating. So how am I going to take that operational data, that information about invoicing, and turn that into something supportive, support data? So data that's going to support some decision making. Then we're going to analyze our support data to generate information. So we're going to turn that support data, so that sum of invoices over the last week, we're going to look at that data and we're going to turn it into some information. Oh, we've done 10% more invoicing this week than we did last week. Okay, now we have some information. Now we have to present it in such a way to make business decisions. So you have to find a way to get it from the query, get it from your result set into something useful. This can be turning it into Excel and turning it into a graph or a chart, some sort of visualization. This can be just sending reports, Excel spreadsheets, PDF documents with information and knowledge in them. Being able to present it so that someone can take that information and create decisions from it. Okay, this is where it kind of gets circular, because at this point we go and generate more data. So we take that information and that business decisions that we can make, and we've changed things around a little bit to generate more data. This could be a circular loop that just goes back and forth, and now we have to store more data, which we then aggregate, analyze, and present. Then we collect more data, aggregate, analyze, and then present, until finally we can monitor the information over a period of time and evaluate your outcomes, what actually happened. The most important part of this whole thing is the last step. We want to use those outcomes to predict future behavior. So we can look at all of the data we've created and all of that aggregation and all of those business decisions we've made and determine whether or not the business decisions did good for our company or did bad for our company. Can we predict future behavior by looking at that data? So while you're looking at data over time or across regions, however you want to break it down into dimensions, this is where you're going to look at that and go, Can we use this information to predict what we're going to do in the future? Should we add more sales reps to this region? Should we pull back some sales reps because we're not doing that well? Should we change our advertising campaign? What can we do here from the information that we have to make better decisions and predict our future behavior? And that is the whole purpose of business intelligence, being able to eventually predict future behavior. Now, you have to do a lot of steps to get there, but when you get to the end and you have all that data and it's all aggregated and it's put into a visual sense so that you can understand it, now we can predict future behavior, do what's better for the company. What is the best choices at this point? So this is the basic concept of business intelligence. The architecture of business intelligence. How is business intelligence created? What are the components and how is it made up? All right, so we have a subset of data. It's external, it's operational data. It's sitting in our database. Cool. First thing we're going to do is we are going to extract, transform, and load, which is the ETL stage. We're going to pull some data out. We're going to munge it. We're going to transform it into something useful, and we are going to load it into our data store. Now, our data store is specifically optimized for analysis and speed. It's our data warehouse, and we're gonna have a little bit more conversation about data warehouse in just a second. But our data warehouse is a different type of database than your regular RDBMS. It's a little different than your regular SQL Server in that it is optimized for querying. It is not optimized for updating and inserting, but it's optimized for querying. The whole purpose of it is to be able to take the data in there and extract it as fast as possible. Your normal SQL Server is not optimized for speed. I mean, it's optimized as best as it can, but it recognizes that you're going to have a percentage of updates and a percentage of inserts and a percentage of deletes, and so it's not expecting 99% of it to be selects. Your data warehouse, on the other hand, is. So it is designed to make things fast for query retrieval. Once it's in our data store, and we can store in either a data warehouse or what we call a data mart, it's a small little subsection of a data warehouse. We can store it there, and then we're going to pull from there and do our querying and reporting. So we're going to pull our data into a query, and we're going to create a report. With that report, we are going to do two different applications of that. We are going to monitor and alert. So are there things in that report that are important? Do we need to keep track of, does this number not reach 10%? Does this number higher than 30%? Is this number higher than 6? Those kind of monitoring to check our values at this point, to make sure that we don't do anything we're not supposed to do, so that we're keeping an eye on values and making sure we don't go too low, too high, whatever those constraints are that we need to keep track of. It could be make sure that our weekly sales do not fall below $20,000 or something like that. These can be those kind of constraints you put into monitoring or analysis or alerting. So we want to alert somebody if they do. We want somebody to know. So we don't want to keep going on with our day thinking everything's hunky-dory when it's not. So that's where that monitoring and alerting comes in. The other is what we call data analytics, where we take the data and we analyze it. We do that aggregate functionings on it. We take the numbers and we turn it into something useful, like a bar graph or something that tells us some information that we can then turn into that visual view. And then, of course, data visualization, which we're going to talk about a little further as well, which is a picture says 1,000 words. You get so much more out of a picture than you do out of just data. So if I can take a picture with a bar graph that shows how my sales have increased or decreased and how my percentages have changed with a pie chart, things like this, they make so much more sense to people than just straight numbers. So this process of our business intelligence, where we have our data, we extract it, we put it into a data warehouse, which we then pull out with querying and reporting. We use that to either monitor or alert and do data analytics, and then create this visualization dashboard so that we can see everything. This whole thing is called business intelligence. This is the architecture of business intelligence following this process. There are tools that we use throughout. So dashboards, I mentioned that one before, monitoring, portals. So we'll use the word portal a lot in computers, where it's a dashboard. It's a way to see into your data. Again, analysis and reporting tools, anything that can draw us graphs or pictures, anything that can take our data and turn it into something that makes more sense than just data. So saying that my sales were $50,000 this week, does that mean anything? Well, no, it's just a piece of data. But when I compare it to other data points, well, in this region it was 50,000, but in this region it was 20,000. Well, hey, then the first region's doing pretty well. Now we're able to do some analysis. Now that we've got some different data points, different areas to be looking at, we can look at week by week, we can look at regions, we can look at salesperson, different dimensions of your data. We can use data mining tools to be able to drill down into your data to find little pieces of information so that we can do something with that. If I wanted to do a bunch of where clauses on my data, I only wanted customers over the age of 50 in Chattanooga, you can do that with data mining. So you can drill down into your data. Data warehousing, again, is the data store that's designed for querying. And then we'll talk about OLAP tools and data visualization a little further. Each of these we're going to cover in different slides to explain them a little bit better. A couple of the components inside of your business intelligence architecture. The first is simply your master data management, MDM. This is the techniques that you use to manage your metadata. So metadata, information about your data, is the definition of all of the data within the system. This is your way of organizing all of your data tables, all of your data, being able to keep track of how they're related, how they're associated, what data is actually in there. Now you could say this is your ER diagram or your UML, but to an extent it's a little bit more than that, because it gives real depth to each of your attributes. Instead of your attribute just being a single field or a field and a type, now we're getting into actually managing each of those field data as far as how do I use them to pull information out. So you may have something that says, date, invoice date. Well, is invoice date important? Did you get paid on the invoice date? Was the invoice date just the date that the guy signed off? Was it the shipping date? Was it the day it left inventory? What does it really mean? And this is where your master data management is going to come in, keeping track of where all that information is. How is it combined? How is it controlled? It's your metadata and organizing of your metadata. The second level is what we call governance. Governing, keeping track of, limiting, control, and managing. This is the part about it where we actually look at the decisions that were being made and make sure that they were good decisions. Being able to have good governance on your business information is important, because if I hand you a report that says your sales are down for 3 weeks and you do nothing about it, that's not very good governance. So governance is simply managing that business health, making sure that the higher ups are making good decisions, that the people in charge are doing something with your business information and being able to make the company better at the end. So being able to control and manage your business decisions and your business health. And then the other one is what we call KPIs, or key performance indicators. The important thing about KPIs is that they're quantifiable. They are able to have a number associated with them. A couple of examples of KPIs are listed here. Year-to-year measurements, earnings per share, applicants to job openings, graduation rates. Each of these are numbers, and you can look at a number, quantify it, and be able to chart it on a graph to be able to say, is this number going up or is this number going down? By giving each of these data concepts a number associated with it, you are able to graph it and chart it better so that you can visualize it. So if I just said students are happier, well, how do you quantify happy? Well, okay, so we asked the same students to rate on a scale of 1 to 10, what is their happiness with this class? And for the last 3 years, the happiness was 3, and now it's a 7. Oh, well, that means whatever we did different this year made the class better. This is quantifiable. We can look at a number and be able to actually numerically see how things are going. So really important part of key performance indicators is that they have to be quantifiable. They have to have a number. When we talk about different styles of reporting, We can do what's called advanced reporting. We can do monitoring and alerting and advanced data analytics. So advanced reporting, getting into more details, having more information in your reports. Monitoring and alerting, like we said before, this is being able to pull out pieces of information that say there's something going on, there's something good, there's something bad, but we're keeping an eye on it. So if we have a high and a low and we exceeded our high, we'd kind of like to know that. If we've gone too low, we'd like to know that as well. So monitoring and alerting does that. And then of course our advanced data analytics is being able to take our data and analyze it down to useful levels. Is this region specific? Is this week to week specific? Is this team specific? Or is it like single salesperson specific? This professor, this college, this town, this city, this county. Locations are big in reporting styles of being able to break things down in data analytics. So a lot of times we like to talk about the evolution of a concept. In this case, we're going to talk about how business intelligence got into and how we started evolving that over time and the trends that we're following. So reasons why we do business analytics, why we do business intelligence. We have integrated architectures. So we have this concept where things are integrated together. The different departments, the different parts of the company are all integrated. We like having common user interfaces so that if you're in one part of the company, your user interface looks the same as others. We want a common data repository, so we want all of our data in one location. And we also have improved organizational performance because everybody in the company is all doing the same thing. They're all part of the same group, the same team, the same data. They all get along together. So organizationally, I can call someone from HR and someone from sales and use the same terms and the same data fields, and they'll all understand it because we all work together as a team. In the 1970s, when things first started with computers, we would start storing stuff in computers, and we had data warehouses at that point, being able to store data, but we created centralized reporting. So our reports were kind of centralized. If you wanted a report, you called a specific department and you got reports from there. All of the reporting was done through one specific area, and it was really, really centralized. Over time, we got into the 80s and we started introducing Lotus 1-2-3, and we introduced Excel, and we introduced different ways of being able to get data into a spreadsheet that you could use at an individual level. You didn't have to go through a centralized reporting to get your data. You could get it yourself, which was great because it was much easier than wasting time waiting for someone else to get around to giving you your data. By the 90s, we started getting into enterprise reporting, where we had generic reports that you could run on your own time, but you could create them and they could be completely enterprise dependent on different departments, the whole company as a whole, or just your department, things like that. We also created the online analytical processing because we started the internet. So we have online at this point. By the 1990s, we have the internet going. And you could start doing reporting through the internet. By doing things through the internet, it suddenly got so much faster. I know it may seem weird, but back in the 80s and the early 90s, if you wanted to report on your sales figures, you would store those in a data warehouse somewhere. If you're, say you're at a school, data warehouse would be somewhere on campus in a big, huge server room, and you wanted some data out of there. You would actually request your data reports, or you would get them every Friday. Reports would finally come in. You get your reports and you'd look at them, and you'd have to look at the data and do something with it at a personal level at your department side. By the 1990s, we had the ability to network to that data warehouse and create those reports in your own department. That online analytics, where you could take data out of the data warehouse locally and start processing it with the invention of the internet, was amazing. This concept of I didn't have to wait for Friday to get my numbers, I could get them anytime I wanted. So that was the starting of the 1990s, beginning of the internet. You can kind of look at the start of the internet as a lot of these things. By the 2000s, they started to realize that having a dashboard or having a portal where you could look at all of your data metrics all at one point was really, really useful. Since the internet was there and we could start making web pages, we could use those web pages to pull data from a data warehouse, process it, create it in a visual mode with graphs and charts, and be able to allow you to do business intelligence in almost real time. This was pretty fast. And it may take a little longer, it might take 2-3 minutes to draw a report, but it would still do it. And it would create this portal for you to be able to view your data. It's the start of the dashboard concept. We also started with the mobile data. So this started sometime between the 2000s and now, where we started being able to get data through mobile business intelligence. You could have your phone, your BlackBerry back in the early 2000s, but your phone now with all of your business data as well. You could do this real time. You could be in New York and your company could be in LA and you were still able to get hold of the data. That was huge, being able to be away from the office and still be able to get data. And then now we have this big data concept, which we've talked about in chapter 14. We'll go into much better of the NoSQL data visualization with your big data. So this is kind of how it's moved along. And it's one of those things where it's moving so fast that people are kind of forgetting how hard it used to be. You know, I need my report today. Okay. Used to be it might take 4 or 5 hours. Now you go push a button and you get the report. It's so amazing. So this is the evolution of business intelligence over time. Now, the trends that we're currently following. We want to make our data storage better. We want to improve it. We want to make it better for querying. We want to make it better for getting the data out that we want and being able to ask appropriate queries, questions of our data, and being able to get that analysis as fast as possible. Creating applications that do our business intelligence for us. Used to be, you get a report, you'd have to import the data and then be able to figure out, well, what do I really want to look at and how is the data formatted? Things like that. We've created the concept of business intelligence as a service. This as a service, the software as a service, application as a service. Now we've created a business intelligence as a service where you can have a service on the internet in a website where you tell it where your data warehouse is, and it will do the business intelligence for you. It'll start running these, and that'll be a service that you pay a monthly fee or so. Being able to do our analytics on big data. So this social media big data is such a big thing because there's so much about what you do that is being stored and kept track of, and how do we take that information and turn it into something to help our business do better. So being able to take our big data and analyze it is huge. And then, of course, personal analytics. So, you're walking down the street and you tell your phone, hey, go look up the price of dog food. And now every Facebook ad has to do with dog food. Because we're going to take personal analytics, we're going to take it on a personal level to individual people and be able to figure out how to analyze you as a person and use that analysis to decide the best way to approach you to get you to use business services. So how do I convince you to go to McDonald's instead of Burger King? How do I convince you to shop at this store versus that store? Well, what are the things that are important to you, and how can I use that knowledge to make everything for you more personalized? So we have the difference between operational and decision support data. When we think of the difference between operational and decision support, your operational data is your current day-to-day real-time operations. You had an invoice today. Somebody came in today and bought something and you needed to store an invoice today. You entered the invoice. That is an operational data. You are doing that to make your operation work. Everything there is going to be current. It is going to be very specific details. This invoice, this line item, this product. We're not going to do a lot of aggregates at this point because we just have a singular point of data. We might do some sums or some calculations if we wanted to get the total of all of the line items, but it's going to be really small. The yields of the aggregation are going to be really small because it's just going to be over a specific invoice or over a specific customer or something along those lines, but it's not going to be huge amounts of aggregation. You can use the regular relational database model with it highly normalized, and it works beautifully because the normalization keeps you from data repetition and it helps you to keep your data straight. So that's really important at an operational level. Most of the stuff is just operational updates and things like that. It's not a huge amount of data going through at a time. So your data volume might be gigabytes, but it's definitely not getting up into the terabytes or the petabytes. It's a small amount of data because it's just daily. It's operational, and you could do operational data for a day, a week, a month, maybe even a year, but you kind of want to stop there. You don't need 20 years of data in your operational data, because everything from last year all the way back to 2000 is not going to change. You're not doing any updates. Decision support data is generally either historical or snapshots. So a single snapshot of the operational data as of today, or historical data, the last 5 years, the last 10 years. Could be time specific. Years is a really big one that we do for decision support data, but you can do it by region, and you can do it by team, and you can do it by a lot of different pieces of information. But it's generally more historic. It is not today's data. It is the last 10 years data. It's generally summarized, so it's not going to be individual invoices. I don't care about an individual invoice when I'm looking at decision supports. I want to look at the sum of all of my invoices. I want to look at the count of my invoices. I want to look at aggregation, summarized data. I do not want to look at individual pieces of data. So when you're looking at decision support data, individual pieces of information, atomic, is really small. You don't really want to deal with that. You want to deal with the sums, the aggregates. There's a lot of aggregations you can do across different levels. It's definitely not normalized, because this is the data that you want to pull out. This is the results set of, I need my customers and my products and, my sales all in the same, the count of my customers, or the total of my sales all aggregated, but it's not going to be really normalized. So although you can use relational databases at this point, sometimes you don't, because it's just not necessary to have them relational to do the data storage. You're not worried about data redundancy, because at a decision support position, data redundancy is not a problem. You're not going to be changing data anyway. And the problem with data redundancy is, if you change it here, you have to change it there. You're not changing anything. So you don't have to worry about data redundancy. So you don't have to normalize your data, which is an important part about decision support data. While the transaction types in operational are usually updates, insert, updates, deletes, the transaction type at decision support is always queries. You're pulling data out. You're not changing anything. You can, and it's possible to change your data, but in general, you're doing querying against your data. You're not updating anything. And then, of course, data volumes. This could be huge. This could be, if your company's been around for decades, this is a large amount of data. Now we're talking about the terabytes and the petabytes. Lots of data goes in there. So it's really important at a decision support that you're looking at large amounts of data. You need that querying ability to go by quickly with large amounts of data, whereas your operational data has smaller data sets, so it doesn't need it to be as query optimized. So these are the different ways of looking at operational versus decision support. When we are trying to find a database for our decision support, so we already talked about our operational support. We're storing that in a regular relational database, SQL Server, it's fine. But when we need decision support database requirements, so where are we dealing with our decision support data? Because we just talked about that, and we don't need it to be normalized, and we need it to be really optimized for querying, and we need it to hold very large data. So how do we handle that? First off, we talk about the database schema. So it doesn't need to be normalized data, is a big thing to keep in mind when you're talking about decision support. It needs to be aggregated and summarized, and it needs to be able to extract time slices. So when we talk about time, we like to be able to give it the last week, the last month, the last year, the last quarter, the last 5 years. So time slices. How can we break this up into individual slices so that when we pull the data out and I say I only want data for this period of time, it can pull that easily. So we need the schema to handle that. Data extracted and filtering. We need to be able to batch and do our data extraction, because there's such a large amount of data that we're going to be analyzing. We might want to do that in batches and be able to organize it by having it scheduled so that we can do it at 3 in the morning where it's not going to affect anybody. It's not going to be waiting around from, if we started at 10 in the morning and we don't get the data back until 4 in the afternoon. Much better if you started at 2 in the morning and have it ready by 6. So being able to schedule your data extraction. Sometimes we need to store data in different data sources. So sometimes it's in a relational database, sometimes it's in a network database, sometimes it's just in a flat file. We need to be able to get that data out and be able to do stuff with it. And then the most important part is being able to filter and restrict your results. So when I take the data and I say, I only want data for salesman John Doe, I need to be able to filter all of the data and get just John Doe's sales over this period of time. And I need that to be quick. So being able to handle that data extraction and the filtering is really important with your database. The last part is the size. Again, data warehousing, data support databases need to handle huge VLDBs, very large databases. Yes, we love our acronyms. A very large database is somewhere from gigabytes to terabytes to petabytes. You hold a huge amount of data in a very large database, and it's designed that way. It's designed to handle large amounts of data. Your regular SQL Server, not really designed to handle that much data. I mean, you think of it as a lot. It could be hundreds of thousands of records, but we're talking about billions of records. So when you look at it that way, you could be storing large amounts of data, and you need your database schema for your decision support data to hold very large databases. You also need to handle two different types of processing. So we do a symmetric multiprocessor. Symmetric being at the same time. Multi-processor, multiple processes running at the same time. So a symmetric multiprocessor or a massively parallel processor. Parallel being multiple processors lined up together, and massive, they're doing a whole lot of work. There's a lot of processors. We're not just talking about one or two processors. We're talking about hundreds. And being able to run that processing, again, we're just querying. We can do parallel processing when all we're doing is querying, as long as we don't change any data. So querying data is pretty good. We like that. So parallel processing or multiprocessing, really useful when you come to a decision support database, being able to hold that. Remember, this is not your normal SQL Server. This is a data warehouse that is designed for the purposes of storing your support data, not your operational data. You don't replace your operational data with a data warehouse. You use a data warehouse or the decision support data to do your business and analytics, but you still have your operational database doing its own job on the other side. Okay, so now we're going to talk about what is a data warehouse. First off, just so that you know the name, so that at some point in some trivia question, you recognize the name. So Bill Inman created the concept of a data warehouse, and what he wanted was an integrated, subject-oriented, time-variant, non-volatile collection of data. So 4 things. Most important, it has to be, actually none of them are most important. They're all very, very important. It's a read-only database optimized for analysis. That's what it's for. When we look at integrated, you can have similar data. In an operational database, you have similar data in different representations, so you can store things. But in a data warehouse, you want to have a unified view of all your data elements with common definitions and representations. This, again, not normalized. We are unnormalized data, and it's going to be integrated in that all of the different data from all of the different departments are all going to be included all at the same time. It's all together because you need information from sales and you need some information from customers at the same time. Everything needs to stay integrated. You might need employees in there as well. Everything's all integrated. So it's one unified view as opposed to having different representations. Subject-oriented in an operational database means the data is stored with the function or process. So it's designed for operations, invoicing, payments, so on and so forth. In a data warehouse, the data is stored so that it facilitates the views of the data and decision making. You might include things that would include invoices, payments, and credit amounts all in the same report because they all are useful for facilitating that piece of data, for that piece of information, for that report. So it's subject oriented in that when you're looking at your data, you need to be able to look at the actual process as a whole rather than individual entities. So again, we don't like to think of it as relational in the sense of being able to break it into entities. This is the data stored in a way so that it's as easy as possible to pull out the information you need. Time variance. Data warehouses very specifically with a historical purpose in mind. You are looking at a data warehouse as a way of storing historical data. So time is generally added to make your data analysis easier. Which quarter are you in? Which month are you in? Which year are you in? Which decade are you in? This type of information is stored when you store it into a data warehouse because it allows you to do those queries faster. So if I wanted to say, give me everything for quarter two from 2012, there's a way of storing the data so that I can just say where query two, or quarter two in 2012 is the time variant, and it pulls me all that data easily and quickly, instead of having to process the date and go, ooh, is this in quarter two? Is this in quarter two? No, it's all just done for you. So time variants are really, really important when you do data warehousing. And the last, of course, is non-volatile. It doesn't change, ever. Data warehousing cannot be changed for all intents and purposes. It can be added periodically, as infrequently as possible, to keep the data up to date, but once it's there, changes are not really allowed. We don't do it unless something really big comes up and you have to change it, but therefore it's pretty static. You can have updates or you can have inserts when you add new data, but essentially you're not changing anything that's in there. When you are looking at your data warehouse, another way of looking at it is a data mart. Mart, in this case, is a small single subject data warehouse. We can break our data warehouse in same way that we fragmented our databases into our distributed databases. We can kind of fragment our data warehouse into different subjects so that you can have a single subject data warehouse that holds all of the data that you need for that subject. So the reports related to that subject all are in one location. If you've looked at this book long enough, you know that we really like our 12 rules. Everything has a 12 rule. And of course, there's a 12 rule for data warehousing. The 12 rules are in your book, table 13.9. You can go find them. Bill and Chuck Kelly came up with this as their rules for how data warehousing is done. Most of them are created based on the relational model rules as well. So the operational and the data warehouse are separate. Data warehouse is integrated, contains historical data over time. It can have a snapshot at any given point of time. This snapshot is a really important thing. I want to know what the data warehouse looked like on June 23rd, 1922. Okay, not 22. How about 2012? There we go. That makes more sense. And you can do snapshots based on a specific date and time. It's very subject oriented as opposed to being relational. It is mainly read only. It can do batch updates, but no online updates are done. So you do batch updates from your operational database. Your operational database tells the data warehouse, but you don't have an application to go access it. It's not like you're going to be going in and doing updates from an app on a website or on a phone. Those are all going into your operational data, and then your operational data will do batch updates every week, every day, every month, however they need to do it. The data warehouse lifecycle is a little different because the development is really data driven as opposed to process driven. When we did our life cycles for database life cycles, we were very process driven. How did the process go? Did you describe your process? This is very specifically data. How is your data driven? How is your data moving through? And it's very data driven, so your process is just a little bit different for your life cycle. It contains data with several levels of detail. So we have current, old, lightly summarized, heavily summarized, different breakdowns of different types of detail. The big thing, number 9, is where we use read-only transactions to very large data sets. We assume a huge amount of data and we assume everything is read-only. Usually has, we trace the data source, transformations, and storage, so that's just held on to. We have the critical components of the environments. The metadata is really important at this point because it identifies everything. It's that developer's dictionary or the database dictionary, being able to store all of the metadata for your data, which is important as the guy building the database, as the guy building the reports. You need to understand where the data is, what it means, and what each piece of data means. So that metadata is really, really important. And then, of course, it has mechanisms for resource usage to enforce optimal use. So you keep an eye on how the database is used and make sure that it's optimized as much as possible. So I keep using this word dimension. And there's a reason for it, because when we got to this slide, I wanted you to already be kind of comfortable with the word dimension. Dimension, 3 dimensions, 3D, 2D, 4D. Dimensions are different aspects of the data. So to visualize data that goes into a data warehouse, we use something called a star schema. And this star schema is a modeling technique that we use to map multi-dimensional decision support data. Multi-dimensional in this sense is which different dimension are we looking at. So this isn't just like a 3D cube. It can actually be a multi-dimensional cube. It doesn't have to be 3, it could be 5 or 7. But it creates a multi-dimensional cube, and it creates the schema from a relational one. So we originally had relational database, but we need to be able to break that down. And so we first look at our facts, either our numeric measurements, our actual values, or our metrics, things like that. And then we break it down into the dimensions. So in this case, we have our sales fact, $125,000. Okay, cool. Our location, what location are they in? So the dimension related to this is the southwest location or southeast location, because that's the location that goes with this piece of data. We also have the time dimension. Time dimension would be May of 2018. So in May of 2018, in the southeast location, we had sales of $125,000. The top one is the product. So this was an HP calculator. What product did we sell in the southeast region at this time that had this sales fact? So you can see how there are multiple dimensions, multiple pieces of information that we want to have that is relative to others. Everything in business analysis or business intelligence is going to be related to other pieces of information. So I want to say, how did this product do in this time and location compared to other products in this time and location? So the dimensions of, say, 3 of these cubes could be 3 different products all in the same location and time. So you can see the 3D Rubik's Cube kind of thing that they're showing here, where we have the sales facts all for the specific product over different time. We have the sales fact over different locations, and we have the sales for that location and time for different products. And all of these tell you about these facts. So the attributes can be the descriptive characteristics about the facts, and you can use those to narrow your searches. So if I want to say in the southeast region in May of 2018, what were the different products and what were their sales numbers? And that would be a piece of information that you could visualize with a star schema to be able to see how those work. The thing with facts, dimensions, and attributes, those are pretty obvious. Attribute hierarchies are the drill down, or what we call roll up aggregates of the attributes. So if we had the location attribute, the location dimension we wanted to talk about, is this the entire world? Is it a specific country? Is it a state within a country? Is it a county within the state? I missed region. We could have done region in there. City, neighborhood, all the way down to an individual house. So you can have this hierarchy of different objects. You can have time, and you could say per day, per week, per month, per year, or per quarter, per year, per decade, so on and so forth. These could be your hierarchies to give you the different ones. If I said calculators, HP calculators, this specific HP calculator, this would be the different hierarchies for products. So you could have products, you could do it by brand, you could do it by product name, you could do it by version, things like this that would be the hierarchies of those attributes. So this is how our star schema breaks down, and it does this 3-dimensional view of your data. Now it doesn't have to be 3. I keep saying 3 because we're looking at a 3, but it's multidimensional. It's abstract. You don't have to visualize it in the sense of you don't have to be able to see it in your head. You just have to understand the concept that all of these attributes can go off in multiple dimensions and be able to give you that piece of information. This is why a regular relational database is not always used for data warehousing, because the purpose of data warehousing is to be able to aggregate based on these dimensions, based on these attributes, and you can't do that with a regular normalized table. We get a performance improvement when we use our star schema. And there's an example here of a star schema that's put in a two-dimensional view so that you can see it. You could draw something like this. I'm not expecting you to draw a three-dimensional view, but this is a two-dimensional representation of a three-dimensional view. We have our product, our vendor, and our time, with our order being the piece of information in the middle. So our order can be three-dimensional representation, all of the products, all of the vendors, and all of the time as being our three dimensions in the different directions. When we do a snowflake schema, which is what this is a regular snowflake star schema, shows the dimensions of the table having their own dimension tables. So each of those dimension tables has their own dimension tables inside of them. So all of the products, all of the vendors, all of the time are the individual dimension tables inside of the order table. So you can kind of see them having that relationship. We like to maintain multiple fact tables. So we store fact tables, which speed up the query optimization. So what are the products for this brand? Store that, store it in a database. With relational databases, we don't want to do that. But with data warehousing, in this case, we do want to store that, because the more data that's stored, the less query joins we have to do, the faster our queries are going to be. So if you think about a regular relational database, we might have 5 joins in here keeping track of all this information, whereas you could store it in a singular table and you only have to do a where clause on it. So where the product equals this, the time equals this, and the vendor equals this, and it's just a simple where clause on a single table. So much faster. Much faster for aggregation. If you're going to be summing up those information, doing aggregation on a single table, so much faster than doing it on multiple joins. And of course, those fact tables are totally denormalized, because the denormalization increases performance. We can also do partitioning and replicating tables like we did with our distributed database systems. So we can break down those tables into the areas where they would be needed most. If we only wanted sales in our sales data mart, instead of an entire data warehouse, we could break up our data warehouse into partitions. We could have replications of those tables so that those are available in the areas that they need. And the big thing to remember with this is that periodicity, the breaking it down into a given time span, the current year, previous years, all years, what is the time span for this table? And there's no reason not to store multiple tables, one for each periodicity that you might need. Much easier to pull all the records out of a single table than to take that one table and do a where clause on it. So we can do that. We can break up our tables, we can replicate our tables to make the information as accessible as possible. We're going to go into a new concept, well, not new, the concept of online analytical processing, or OLAP. Online analytical processing is the way that we take our data out of our data warehouse and process it. So there are different ways to do that, and the basic architecture is listed here. So again, we have our external and our operational data. It hangs out where it is. We do our extraction, transformation, loading, go into our data warehouse. The important part here is that you have alternate direct access of operational and data warehouse information at the same time. If your data is in the data warehouse, pull it out of the data warehouse. If your data is in the operational data, go get it from the operational data, which means it's much faster to just pull all of it from the data warehouse if you're doing older reports. But for current reports and stuff like that, you may have to take them from both, and that's okay. So your OLAP engine is the front end to the data warehouse. It's the way to get information out of your data warehouse. It's the analytical processing part of it. So we have in there some data processing logic and some analytical processing logic. And this is, where do we get our data from? We got to get all of our data, and we got to get it all in the right place. So we got to go process all of our data. And we're going to analyze all of our data. This can include some application plugins. So you can do this straight out of Excel. You can do it straight into Access. So Access is the standalone database that can sit on your desk. You can have that pull from data warehousing. And then of course you can have a GUI individually. It's just your OLAP GUI that you can create for data analysis. And it uses that processing to be able to get the data where it needs to go and do all of the processing. Once it gets its data, it can do any of the 5 things listed on the side. It can do your advanced reporting, it can do your spreadsheets, it can do your regular OLAP reports, it can do your dashboards, and it can do your mobile business intelligence. So being able to get the information on your phone that you need. When we look at this, we have our multidimensional data analysis. Remember, multidimensional in the sense that it's going to go across multiple dimensions, not like the TARS. We're going to be getting data from those location or time variants or product variants, whatever that multidimensionals are that we want to use. We're going to do our data presentation, our data aggregation, classification, and data modeling. This is the stuff that we have to do in our multidimensional. How are we going to model our data? How are we going to aggregate it? How are we going to classify it? With our database support at this point, we need access to all of the different databases. It might get a relational database. It might use a flat file. It might use internal. It might use external. It has to get it from all different locations. It has to access the data warehouse, and it has to be as fast and consistent as possible in its query response time. The concern you have is it's all about speed. You have to get the data as fast as you can so that you can spend the clock cycles doing the analysis on that data. So you don't want the data extraction to be the hardest part of your information. You want to be able to get the data as fast as possible. And then, of course, with any system, you need an end user interface that is easy to use. If it is really confusing for your end user to actually get your report, they're not going to use it. So this is important that you're going to create a user interface that works really well, that the people understand and is usable. So we have to ask the question, we need to create a data warehouse. Which type of database do we pick? So we need to be able to do this OLAP. We need to be able to do our online analytical processing. Do we pick a relational database or do we pick a multidimensional database? So we haven't really discussed what a multidimensional database is. So we're going to start with the relational one because I think that'll make more sense to you. You can have multidimensional support in a relational database when you create a star schema, which is fine. We've shown you the star schema. You can probably visualize how you would create the database and it would work fine. As long as it is optimized for queries, not for updating, and it's easy for most people to understand if they already understand the current relational database. They already understand SQL Server, so let's put it in SQL Server because we get it. We understand how to use it. We know what the tools are with it. If we're already using Oracle, let's keep using Oracle because the people that are going to be accessing this already understand it. So you have that technological issue of whatever your users are comfortable with. So a lot of companies pick relational databases at this point just because it's the one everybody gets. You can optimize your relational database for multidimensional data, for star schemas versus basic normalization. You don't have to have a normalized relational database. You can have a non-normalized relational database. It's just not the way we do it for the most efficiency in redundant data, the way we talked about, but you can do it. You can also have your basic relational database, like your SQL Server, supporting it for very large databases. You just have to change some of the schematics so that you prepare for there being large amounts of data across multiple locations. And it's really kind of an obvious choice for for companies that already have a relational database in place and they just need to create a secondary database for their data warehouse. They can do that and they'll just design it a little bit differently when they build their database. And that's okay. There's not a problem using that. However, if you want, we can go over to the multidimensional side. At a multidimensional online analytical processing database, so the database for your OLAP, we store the data as a 3D data cube, and we actually call it a cube. It has an X, a Y, and a Z axis to the cube, which are coordinates that hold data at given dimensions. So you can visualize this as a visual cube with 3 different points to get to it, as opposed to 6 different points, which is another conversation. But the data must be static. Very important, the data stays static. It can be held in a cube cache. So in memory, we can hold that cube cache that holds all your different cubes together. The important thing to think about when you're thinking about a cube is the sparsity. So the concept of I have how many different possible values in this cube. Well, what if I don't have a location dimension? Well, I don't do anything with that corner. What about, you've got your 6 different points that you can pick from in any specific cube. What if I'm only filling in 2 of the points? So you can have a sparsity. It's not uncommon to have 50% or more of the cube cells not being populated because you don't have a data point at that face of your cube. And that's okay. That's expected with data cubes. You're not expected to fill in all 6. You can, but you don't have to. Multidimensionals are best for large databases, obviously. So the larger your database, the more likely you're going to lean towards a multidimensional. And it's also the fastest with large data sets, as long as you have predefined dimensions. So as long as those dimensions are already predefined and you've got those set in there, you say, okay, I'm going to put this in this dimension, this in this dimension, and it's all going to be good. It's faster than a regular relational database. Is the difference in speed that important? Depends. It depends on your data. It depends on your needs as your company, whether or not you need to go with a multidimensional OLAP, or if you can stick with a relational OLAP and use that database instead. So speed difference, yeah, there's a speed difference, but is it a significant speed difference with the data that you have? All right. Basics of data analytics. I've used the word a dozen times today alone. Analytics, mathematical, statistical, and modeling techniques just to get your knowledge from your data. Being able to take your data and do what I call munge. Take your data, mix it all up, do summations, do counts, do sums, do averages, do mins and maxes to get the knowledge that you need from that. You want to min, what was our worst month of the year for sales? Max, what was our best month for the years? Those kind of things. 2 different ways that we can do this. The first is explanatory analysis, what happened, versus predictive or predicative, depending on how you pronounce it. Predictive, I like predictive because it predicts what will happen. So predictive. When we do data mining, the purpose of data mining is to uncover your hidden patterns or trends. They're not obvious when we do data mining. Sometimes it is, sometimes it's not. So when we do data mining, we do 4 different phases. The first is preparation of our data. Then we classify our data. We start breaking it down by class and grouping it together. Then we turn that piece of information into knowledge, and we use the knowledge to give us a prognosis. What are we going to do with the data now that we have it? What can we do to change things? You can do data mining with guided, where a user is actually picking the different points as you go along, or automated, where the system will figure out where to go next. So different ways of data mining. When we do predictive analysis, it's similar to data mining. It's almost the same process, but the purpose of it is to use data mining to predict future behaviors. The examples that we use are like credit ratings. Why do we have credit ratings? Credit rating comes up with a number, a singular number, and that credit rating is supposed to be able to predict whether or not you're going to pay your loan back. Like one number to determine if you're going to pay your loan back? Well, they take into account a whole lot of information. They look at people, hundreds of thousands of millions of people over time, and people that do the same things you do, and do they pay their bills back? And we use that to determine if you're a good credit risk. Google Ads. When we do Google Ads, we're going to take things that you do and use that to predict what are you going to buy in the future. So predictive analysis, being able to predict the future from the past data. I'm sure you were wondering if we were ever getting into any SQL. Yes, we are. So SQL Server, actually Oracle SQL Server, MySQL, they all have analytics built into them. Analytics became such an important part that both SQL Server, Oracle, MySQL all put in analytics in their SQL queries. So either Transaction SQL or Oracle SQL, everything, all of these use analytics. And we have 2 different ways to do this. The first is what we call roll-up. With roll-up, we add it to our group by. So in SQL Server, we say group by, whatever our group bys are, and then we say with roll-up. Now you have to have an aggregate somewhere in there. So in this case, we've done our vendor code and our product code, and then we have our sum of our sales for total sales. So we have our total sales, and then these different pieces of information. And we're going to say with roll-up. When we do with roll-up, it is going to sum subtotal by the first group by. So in this case, the first group by was the vendor code. So you're going to see that it's vendor code 21225, and then these are different product codes. We're going to do the total sales for each of those. And then we're going to have this value where the product code is null. That's the subtotal. So when you do your check of your data, the thing where it's null is your subtotal. Then we go all the way to the bottom and we see that both the vendor code and the product code are null. That's your grand total. So that's the total of all of your sales in a single SQL query. You don't have to do the math. It's done for you, because that's how often analytics are done. Being able to get all of the records, including the subtotals and the grand totals, all in one SQL query. The other one that we use is the cube extension. And in this one, we do individual subtotals by product code. I've cut this because it's a little bit big and I didn't want to have the whole thing there, but you can see any place where there's a null is the subtotal for that product code. And then we end up with a grand total of everything. So that was the 2252, same as the other page. And then we have the subtotals by vendor code. So we have subtotals by product code, subtotals by vendor code, and they give you both. The cube in the concept of we want the analytics for both product code and vendor code in the same query. Once you get all of this data, you can import it into Excel, play around with it, do some charting on it, do some graphs and some visualizations. So these are the two extensions that we have with SQL Analytics and I've given you the examples of SQL Server. In the book, they use Oracle's version, which is just a little bit different syntax. Same concept and same values, just a little different on the syntax. And I wanted to give you an example with SQL Server syntax. This database, by the way, the sale company DW data warehouse is in D2L. So you guys can go download that and import it into your SQL Server so that you can play around with these queries. Materialized views are a really cool, amazing concept that only really exists in data warehousing. Most SQL servers don't even give you the option of a materialized view. They allow you to do views, and I don't know how much we've talked about views. I feel like we haven't touched on it enough. Views are dynamic tables. So I can write the query, I can save the query, and then I can do select star from this view name, and that way I don't have to write the whole query every time. So you save it, it's a saved query. Materialized views are a view where it actually saves the data. So it saves it into a dynamic table that's similar to a view, but it saves the data directly so that when you want to pull data out of the materialized view, it's in a table. You don't even have to run the query again. It's done. When we do it, it not only runs saves the query, but it stores the result in a table so that it can be queried later. You can choose when is it built, if it's built immediately or if it's deferred, and then when is it refreshed. And this is where it gets into a fast refresh. Every time you update something, it updates only those updated rows. A complete refresh refreshes everything. And then a forced refresh is where we tried to do just the fast refresh, but if that didn't work, then go do the complete. And you can tell this is an example of SQL Plus for a materialized view in a data warehouse with the materialized view syntax. Again, this is not an option in SQL Server, so don't even try it. You have to use the data warehouse to use it, so it's not in there. You can do a view, by the way, and views are something we really should talk a little bit more about when we talk about SQL statements, being able to store those queries. But in this case, it's a materialized view. I wanted you to be able to see it so that you could see how it was created and know that that is something that is an option when you're using data warehousing. The last section before the end of this chapter, I know it's been a very long one, is visualization. Visualization, one of the most important parts about data warehousing, because if you think about data warehousing as a way to get data out so that you can make business decisions, you need the people to understand what the data told you. And sometimes giving people lists of numbers doesn't do it for you. So visualization is the process of abstracting data to provide a visual representation that enhances the user's ability to understand and comprehend the meaning of the data. In other words, graphs and charts. Graphs and charts are fabulous. Dashboards are fabulous. Anything that gives you a visual representation of your data in a way that makes it easier for you to understand what happened. The examples that we have here are just Excel, Tableau. Microsoft has a Power BI, Business Intelligence. There's a couple of others that are available. Tableau has a student version that has a free year, a full year, full thing as a student. So you can go get the student version of this and go play around with it. With visualizations, we like to do pivot tables and pivot charts where we show pieces of information down one side, pivot and pieces of information down another to show that two-dimensional aspect to it. You can also do your charts and graphs in 2 dimensions, which helps you to visualize. Like in this case, you can see the pieces of information and how they are represented. We like to do comparative sales volumes, market penetration, being able to view maps with different sizes. If you've looked at the COVID map, you can see the different visualizations of how big these different areas are where there's outbreaks. So those are really important. Actually, if you go to Tableau, they have a COVID dashboard that you can see, and you can see how you've used Tableau to do it. The important thing with visualization is pattern recognition, spatial awareness, and aesthetics, being able to use the colors and the shapes to show pieces of information. We've made some data here red. Red is bad. Red is scary. We don't like red. Oh, here's some more information that's blue. Blue is nice. Blue is pretty. So you go into those colors and shapes, being able to see things and visualize them. Is this a good thing or a bad thing? People react to that. And then, of course, qualitative and quantitative. Quantitative, we talked about, numeric. It's a number. It's a piece of information. But qualitative can be nominal or ordinal. So it can either be ranked or it can be given a number. And being able to do nominal versus ordinal in your qualitative. How are these done? Are they done in order? What is the most? What is the least? And whether or not it can be ranked by any number at all, whether it is an on or off, those type of things. So those are things that are more qualitative. They're qualities as opposed to quantitative numbers, quantities. So being able to keep those straight with your visualization, really important. This is a great chapter actually, because they give you a lot of examples. And again, I do recommend that Tableau student thing. You're going to need it for number 13 anyway. We made it to the end of the chapter. Very long chapter. Couple of things in summary. BI stands for business intelligence. Okay, we got to stay intelligent. Decision support systems, our system to handling our decision supports. Operational versus our decision support data. This is the operational data versus your data warehouse. Your decision support data could be part of your operational data, but your operational data is usually not where all of your decision-making data is held. Data warehousing or data marts, which are optimized for querying, not updates. Your star schema, if you want to do multidimensional data. Your OLAP, online analytical processing. Data analysis or analytics using data mining. You've got your preparation phase, your classification, turning it into knowledge, and then using that knowledge to create your prognosis. Your SQL analytical functions of your rollup and your cube, and then of course data visualization. Okay, let's get into your homework. Because I do want you to be working on your final at the same time, I have not given a whole lot of homework. There's about 6 terms in the review that I want you to go over, a couple of examples that I want you to just kind of play with. I could have done all 30. No, I figured 6 was plenty. So that was fine for your review. For your problems, 5 through 12 use the sales company data warehouse to do some analytics. And I want you to do those. So that's 5 through 12. And then number 13 is your open-ended one. This is kind of take some data and show some analytics. I recommend that you go get the student version of Tableau, but you can do this in Excel. In the book, there's a lot of examples of where you can get data. So just generic pieces of data. What do you want to know? How many car accidents in Miami last year? How many people graduated from college in degrees in computer science and had jobs when they were done? Different pieces of data analytics and being able to take some data. So they've given you some examples of where you can find data, just raw data. Be able to take that data, import it into Excel, Tableau, something like that, and be able to create a single visual dashboard for me. It doesn't have to be huge. It doesn't have to be a huge amount of data, but I do want you to kind of play around with analytics and being able to do that visualization. The more experience you have with this, you can throw it on your resume. It makes it so much better if you are ever in a situation where you need to create reports to be able to say, I know how to visualize data. I know how to do data visualization from a database. Okay, so have a fabulous weekend. Enjoy this chapter. It's a lot of data in the chapter, but hopefully this video helped you to get through it faster. So you can skim over it while you were watching, something like that, and reference back to it if there's anything you missed. Call me if you need anything. Have a great weekend.